Okay, this is our second class on competition. We are talking today about the sort of algebraic relationships between two competitors, so that we're going to be able to visualize the relationships between two competitors and show when we might see coexistence versus competitive exclusion. So we're going to model these population dynamics. And we're starting with the logistic population growth model equation. In the predator-prey equations, we did something a little bit different. We didn't specifically model with K. We thought about the predators imposing restrictions on the prey by eating them, and the prey imposing restrictions on the predators by either being available or unavailable to be eaten, or being easy or difficult to catch, or how much the predator could convert those resources of the prey into new predators. So in a way, we modeled those kind of restrictions or limitations, but in a different way than we're going to do here. Okay, so remember, when we're thinking about K, carrying capacity, this is in the units of numbers of individuals, but it represents resource availability. So K is the number of individuals that the environment could support. Because we've got two species here, we're going to have two N's. We're going to have N1 as the number of individuals of species 1, and we're going to have N2 as the number of individuals of species 2. We're also going to have two carrying capacities. How many species 1 individuals could the environment support? How many species 2 individuals could the environment support? And those numbers, those Ks, could be different. We could have two species that differ in their resource use efficiency, or how much resource they need to use. So our environment might be able to support one number of species 1 and a different number of species 2. So what we want to model is the space, the resource space taken up by each species and the way that affects the other one. So if we've got some individuals of species 1 and some individuals of species 2, how is the resource use of species 2 affecting how close species 1 is to their carrying capacity or running out of resource? For species 2, how is the resource use by species 1 influencing how close species 2 is to their carrying capacity? That all sounds a little abstract. I think as we move forward and move into the equations, it's going to start to become a little concrete. It will probably kind of get easier and hard a little bit. It's going to kind of come into resolution, and then maybe you're going to lose it. So I strongly encourage you to take your time with this recording resource, for you to take notes, to write down the equations, go back and re-listen to parts that don't make sense. Really take your time to kind of understand what these equations mean. So we're going to define what we're called competition coefficients. We're going to have two of them, alpha and beta. There are other ways of representing these that you might see if you watch other videos and things like that, and I'll mention that when we get to them. So essentially, we're going to use these coefficients to convert individuals of species 1 into individuals of species 2, so that we can say how close species 1 is to the carrying capacity, and vice versa. Convert individuals of species 1 into species 2, so we can say how close is species 2 to their carrying capacity. Simple, right? Something is very weird with this slide. Okay. Oh, yeah. I changed it for a reason that we don't have to talk about. I'm going to hide these two and go back to this one. Maybe. Show, unhide. All right. Okay, let's imagine an environment where we have two kinds of individuals. And for the purposes of this illustration, let's just assume that rabbits and squirrels use the same types of resources. This isn't going to be completely true. There are some things that only squirrels might access and some things that only rabbits might access, and that might give one or the other an advantage. And in one environment compared to another, but we're going to just sort of ignore that amount of complexity. So let's imagine that we've got a space, an environment that would support 100 rabbits if there were no squirrels using those resources. Similarly, this space would support 200 squirrels if there were no rabbits there using those resources. So from this information, these two carrying capacities, we can calculate the competition coefficients, that alpha and beta. So we can calculate alpha as the number of rabbits that each squirrel is worth. Right? So alpha is our coefficient for species 1. Species 1 is rabbits. So alpha is in the units of species 1 over species 2. We're converting 2 to 1, species 2 to species 1. So if we have one squirrel, what do we multiply by one squirrel to get the number of rabbits that would use that same amount of resource? It's 1/2, or 0.5, okay? So again, alpha is in units of, in this case, rabbits per squirrel. The number of rabbits per squirrel is 1/2, or 0.5. Okay, so we're converting squirrels to rabbits. We're going to go the other way with beta. Oh, sorry. I'm going to show you the equation first. So again, we're starting with the logistic model as our base. On the far left-hand side of the equal sign, we've got delta N1 divided by delta time, or dt. So the rate of change in the number of, in this case, rabbits, the number of individuals of species 1 relative to time. And this is equal to, first, that intrinsic growth of species 1. R1 times N1. Births minus deaths times the number of individuals that are in the population, right? How much is that population going to grow, ignoring all other factors. Then the logistic growth model has us multiplying this by a coefficient that relates to how close are we to exhausting all the resources, how close are we to being at the max number of individuals. The closer we are, the slower we're going to grow. So in our original logistic model, we didn't have that thing that's in the green circle. We just had 1 minus n over k. And n over k is our expression for how close we are to carrying capacity. If n and k are the same, we are at carrying capacity. We're subtracting 1 from 1, and we're multiplying Rn times 0. We're not growing. Write that out for yourself if you need to pause and write that out to remind yourself of that. If n is very small relative to k, that amount in parentheses is almost 1. We're subtracting almost nothing from 1. And so we're growing almost as if we were exponentially growing. Okay, so that's a logistic growth model. What we're adding here is this alpha n, this conversion of squirrels to rabbits in this case, of species 2s into species 1s. So we've got the amount of resource that our species 1 is taking up, and then we've got some additional amount of resource that our second species is taking up. And all of that relates to our proximity to k, and all of that relates to then, or influences, our growth rate, our actual realized growth rate. So for the other direction, converting species 2 to species 1, our units are opposite. Number of squirrels per rabbit. Number of squirrels per rabbit is 2 over 1, or 200 over 100, or 2 in this case, given these numbers. So that's beta. How many squirrels could be supported by the amount of resource that rabbits are taking up? So if we had 200 rabbits, that space could support 400 squirrels. Sometimes, as I mentioned, you'll see these coefficients just sort of given as something else. You might see alpha with a subscript 1, 2. That's the way we've defined alpha here, the influence on species 1 of species 2. And then beta sometimes is then expressed as alpha 2, 1, the 2, 1 being in subscript, the effect on species 2 of the number of individuals of species 1. So if you are looking at other things, you might see it expressed that way. The formula is going to be just sort of the mirror of what we did for species 1. So dn dt, but the n here is species 2, is equal to the intrinsic growth rate of population 2, species 2, the R for squirrels is probably going to be different than R for rabbits, times the number of squirrels that are in that population, species 2, N2, times that parenthetical 1 minus N2 plus this conversion factor times rabbits. So the number of squirrels plus the effective number of squirrels. They're actually rabbits, but if they were squirrels, how much resource would they be taking up? All of that divided by carrying capacity. How close are we to carrying capacity, and what effect does that have on our intrinsic growth rate? Okay, so those are the equations, and from this, we're going to be able to create a figure that will allow us to predict the outcomes of competitive interactions.